So, I'll be talking about Python, specifically how to make experiments in that. I'll introduce specific tools in a second. But first, let's talk about what we're going to talk about. I think experiments are really easily creatable by programming yourself and scripting them. But I know I won't be able to convince everyone, so I'm going to highlight this one alternative to it at the start. I'll then tell you about how object-oriented programming is, and then we'll learn everything about Python in 15 minutes. This is OpenSesame. OpenSesame is not a programming language. It is built on Python, which is a programming language, and it's basically just a graphical interface to make your experiments. Super useful. Don't necessarily have to do programming. Just drag a few elements onto a timeline. All sorts of options that you tend to normally use in psychological experiments, like visual stimuli, auditory stimuli, trial sequences, whatever you name it. And it has thousands of users already. That's based on downloads, update checks, and also the forum, which is super active. Built by Sebastian Matteau primarily, and a whole bunch of other people that have joined the team since. In addition, you have cool options within OpenSesame as well for doing eye tracking, actually scripting something if you find that the visual tools are a bit too limiting. And also we have extensive testing on how accurate this thing is timing-wise, and it is very, very accurate. Cool, so now on to the actual programming, because that's the goal for today, to actually get some programming done. And I thought I'd start by giving you a little overview of what object-oriented programming is, because although you might not use it, this is what most of the Python toolkits are based on. And it's great, because essentially it wraps the functionality that you want to use into objects that you don't have to think about. You can just use them as they are. So display, for example, display would be an object. Its class name is display. And when you want to create a display in your experiment, or want to use a display in your experiment, what you'd likely do is initialize it by just specifying the things that you care about, like the resolution, and maybe what kind of backend you want to use for presenting stimuli. So let's say Sakaba in this case. And then, once you've created that display, the only thing you want to be bothered with is telling it what to do. So it has some properties that you set, and after that you interact with it through its methods. So you could, for example, have a method like fill that just pre-prepares a screen in the background, and you could have another method like show that just flips the screen and presents the image. You don't want to bother with how exactly the software makes it so that an image appears on the screen. You just want it to do that, right? So a lot of the libraries that are available in Python use this kind of approach, which takes all of the more specific programming kind of things out of your hands and just lets you deal with the very abstract notion of creating an experiment. There's obviously more than just a display. In this case, I'll present PyGaze, which is one of the toolboxes available for creating experiments. Which, for example, has a display type, but also a screen, which is a set of stimuli on a fixed image, like a canvas you can draw on, essentially. Keyboards as well to interact with peripherals. There's also mice and eye trackers and all that kind of stuff. So to see those in action, I'm going to run through a experiment. Last time we did this here, it took about 6 hours, and that's not necessarily the time that we have here. I have about 11 minutes left, so let's see how far we get. The idea is that we're going to start with just thinking about what we need. And there were some images on here, but they somehow disappeared. Anyway, what we need in an experiment is, for example, a display to show our stimuli, an eye tracker to track where people's eyes go, a keyboard to log responses from a participant, and a log file to write what we've learned from the participant, and maybe also some trial parameters in. So that's what we're going to do. Imagine that those four are on here, like this. Oh, there we go. Oh, they are on there. Okay, sorry. So the display is, in computer terms or in Python terms, this. So you basically initialize it with a simple call to this thing over here, which is called the class. And you just initialize it by giving the parameters you want to use, and then your display is ready for you to use. A similar thing is true for your eye tracker. You just initialize it by using this eye tracker class. pop the display in there because there's a few things that the eye tracker needs to do to the display, like calibration routines, presenting dots that people look at. Your keyboard is very similar. You just initialize it. You tell the initializer what keys you want to use later on, and you tell it what the default timeout should be. You can change these things later on as well. And then we have our log file, where we just provide the name for the log file, essentially. And that's it. That's our first 4 elements. So the point of this is not so that you can write along and write your experiment. The point of this is just to show how relatively easy an experiment can be if you're using Python. So let's say we want to do this in an MRI scanner. We also want to actually incorporate the MRI there. And for that, we recently built a trigger box that works both in the MRI and the MEG within the CBU. If you want to use it, it's on GitHub. You're very welcome to. If you're not familiar with GitHub or don't know where the CBU GitHub is, just send me an email and I'll point you in the right direction. We're going to use that. It's initialized like this, literally just like this. All right, and then the actual experiment is going to be this. And no, I didn't say it was a good experiment. We're going to present these images to a participant, and the task is to classify what the cat is. So you might notice that there's this cat, which is also this cat, and also this cat, and it's different from this particular cat. So you press one button for cat A, and you press another button for cat B. Now those images, they are files, in this case PNG files, and basically the only thing we need is a Python list, which is these square brackets, and between there we have a bunch of strings that indicate what our file names are. So with this, we know enough about where the files are to be referring back to them. So the next thing we want to think about, because this is basically the entire initialization of the experiment, we need nothing else than this. The next thing we want to think about is how to, what to do in our trial. So within every single trial, we want to start with a blank screen that people look a bit like, get that bold response back to baseline. Then we want to prepare an image, because image drawing takes a bit of time. You want to do that during a time that is not time critical during your experiment. So we want to pre-prepare this. Then we want to wait for the MRI trigger to give us a signal that we can go, wait for the sync. Turn on the eye tracker so we can monitor what the eyes are doing throughout the trial. Present the image on the screen. Then wait for a button box response within the scanner, which can be one for one cat, the other for the other cat. Then we want to basically remove the image from the screen again. We want to stop the eye tracker, or at least temporarily pause the recording of eye movements. And then we want to log all the things that we've learned, including the timing throughout the trial, as well as the response. Seems super complicated, so we're going to run through the typical commands that you would use for this. The first is to say, I'm going to fill my display with absolutely nothing. So there's a function called to fill, no arguments given whatsoever, and that just fills the display with completely blank, just a default background color. Then I'm going to call this show function for my display, and that basically says whatever I pre-filled my display with is now actually on the screen. You get a timestamp back that indicates what the time is that the screen went online. Then I'm going to say I'm going to create a new screen, which is that new canvas that I can then use to draw on. I'm going to draw my image, and I'm going to put in the image name as an argument there. The draw image function automatically draws in the center, tries to find where your image file is, and draws it on there. So it's super easy to use. It's customizable by giving in an actual position of the image, maybe giving a different scaling, but this is the basic thing you need. So now I have this image screen pre-prepared in the background. Then I'm going to call the wait for sync function on my MRI trigger box. It gives me the timestamp of when it was triggered. It also allows you to put in a timeout potentially if you want that, and then it tells you whether a timeout occurred or not. This is just telling you whether a trigger occurred or not. Then we want to start recording on the eye tracker, which is basically just telling the eye tracker, start recording, no inputs whatsoever. In the background, just make sure eye tracker starts up, start writing data to a log file, and record eye movements. You don't have to worry about it. Then I'm going to present my image by saying to the display, fill your buffer essentially with this image screen that I pre-prepared. That's super quick. And then I'm going to call show, which puts this image screen actually on the display. and it gives me this timestamp of when that actually happened. Same as here, but now we actually have something. So now we have our image on the display. After that, I'm going to ask my MRI trigger box to wait for a button press, which literally does that. It waits until a button is pressed on the button box in the MRI. It gives me back the name of that button, and it gives me back a timestamp of when the button was pressed. After that happens, I can remove my, my image from the screen. So I again say fill with nothing, which is pre-preparing a blank display. And then I call show to put that blank display on the screen. Gives me again this timestamp. And then I can tell the eye tracker to stop recording, which is literally just a stop recording function, no inputs whatsoever. And then I can log this to my log file, which is literally saying log.write and then a list of all of the timestamps. Probably we should have included the button here as well, because you obviously also want to know what the button is. So that's your trial sequence. If you put it in order, it looks like this. That is one trial. If you want to run through, say, all of the images that you have to indent that and add for a for loop that basically runs for the eye, that is iterated on every iteration of the for loop. It's 0 at the start, and then 1, 2, 3, and so on. In range and trials. Now, this range function just basically makes a list of numbers that starts at 0 and ends with the number prior to this. So we don't yet know these end trials, so we're going to compute them by just taking the length of that images list. That was the list that had all of the image names in there. So this is running all of the trials. Still looks really, really simple, I'd say. Then, to end your experiment, you just say, I'm going to make a new canvas, I'm going to draw some text on there. The text is thank you, and you can specify the size of the font as well. You can then present it on the screen again, like we did before. This should have been end_screen. And then you can close the connection to the eye tracker. You can close the log file as well, so that all of your data is neatly saved. And then you just wait for a key press from the experimenter to close down the whole experiment. So our complete fMRI and eye tracking experiment now is under 30 lines, and as you've seen throughout, actually reasonably non-complex. There wasn't anything where you had to compute how to, put on your image from image file to RGB coordinates that your screen got, would be able to understand. You didn't have to program in a sequence that waited for the MRI to send you a syncing thing. You didn't have to program the low-level interface that allows you to connect to a button box. And basically, you didn't even have to do the eye tracking yourself, which is quite significant because just the calibration normally takes about 50 lines of code, and that is already well simplified. So using these very simplified toolboxes in Python, it becomes actually quite easy to program your own experiment. So in conclusion, Python experiment building can be a lot easier than you might have expected at the start. And even very complex stuff is relatively okay-ish to do. There are specialized open source libraries available, so I presented all sorts of stuff in Pygase in this case, but there's other stuff as well, like CyclePy and Pygame, and they all have similar object-oriented interfaces. And not necessarily relevant for all of you, but for those who want to do experimenting at the CBU with the scanners, we have Mac trigger codes, we have MRI trigger codes, and all of the stuff is now actually installed on the scanner computers. So we can start doing this en masse. So with that, I'd like to say thank you to the people who developed Python, which is initially Guido, but literally a whole army of people. Sebastian for creating the OpenSesame thing that I mentioned before, for Johan and Howard in particular, but also the other people that manage the MAG and MRI units, and also for the two cats that have explicitly consented to be part of this experiment. Finally, before I close down, if you are interested in using Python and also interested in sponsoring my beers, there's a book that I never really talk about, but there's a book and it teaches you the basics of Python, particularly in experimental psychology. So it tells you how to develop experiments. It also tells you how to analyze those experiments, and it starts from literally zero knowledge whatsoever. And that's me done with 5 seconds left. Thank you.